Hey AP Physics peeps, so today we're going to launch into air friction or drag, and I want to give you just a pre-lab on the coffee filter lab that we're doing. So whenever we have an object that is falling or an object that is driving or moving through air, we have air friction. Remember in the past we have totally ignored that and said we're going to ignore air friction, but today we're going to conquer this. So if you picture on the right here, you see that we have the skydiver. We would say that the skydiver has this force of the drag that is acting upward against her and the force of gravity that is pulling her down towards the earth. So I would say that that drag is proportional to her velocity. The faster she gets, then the bigger that drag becomes. So you can think when she first jumps out of the plane, there's not going to be a whole lot of air friction on her, but as she falls towards the earth, it's going to get greater and greater and greater and greater. Remember that the way we can get rid of this proportionality sign, this is the Greek lowercase a or alpha. It is written as a 3/4 of an infinity symbol. So the font doesn't typically come out very good, but whenever you draw it, it's sort of that 3/4 of the fish symbol, basically. The drag then is proportional. The way we get rid of that proportionality is to add a constant. In this case, that constant I'm going to call an uppercase B, and it's the proportionality constant that depends on the shape of the object and the density of the fluid. So we'll talk about that a little bit later when we get to the end of the lab, where we can plug in and determine, well, what is this B value? And if we determine the shape of our coffee filter and the density of the air that the coffee filter is flowing through, we can see how close we were on that B value. So to begin with, if I look at the lady again who is skydiving here, I have an F equals ma, and there are two situations that can happen in this case. When she first jumps out of the plane, she's going to have a force. I'm going to draw my force diagram up here because I need this space down here. There's going to be the weight that is pushing down on her, the force of gravity, but then the air friction is going to be fairly small on her and steadily increasing bigger and bigger. In that case, we're going to say that the weight minus the drag is going to give us the acceleration of her being pulled towards the earth or accelerated towards the earth. Now, as that air friction, as she picks up her speed, that drag gets bigger and bigger and bigger until eventually the drag is equal to the weight. And in that case, we would say there is no more acceleration. So the two things on the left, those two forces, they have to be equal and opposite. And that's what we would say when the object hits terminal velocity, the drag up has to be equal to the weight down at the terminal velocity. We're going to talk about this, but it's super complicated, so we're going to wait until later. What we want to talk about in the lab today, the coffee filter lab, is this terminal velocity value. So when I look at the terminal velocity, Fg is equal to the drag, I can plug in those two equations that I know automatically. I know that the weight is equal to mass times gravity. And from the previous slide, we said that that drag force is equal to the constant times the velocity to the n power. Now, what we want to do in this lab is we want to determine what is that n power. It is some integer, a positive integer, and we want to know, is that 1, is it 2, is it 3, is it 4, is it 259? So how do we mathematically remove that exponent so that it's easier for us to determine? And the answer goes back to one of your math classes, logarithms. So there are two identities that we're going to use to pull that n out of the exponent. The first one is, if you remember, the natural log of any two variables times themselves is equal to the natural log of the one variable plus the natural log of the second variable. Then the second part to that is the natural log of any variable to another power is equal to the power times the natural log of that variable. So that's the way we can pull the exponent to become a coefficient in the front. So if I go back to my equation, mgbvn, then I can take the natural log of both sides. I look at this bv to the n, and it looks very similar to this xy. So I can use that to pull them apart and say the natural log of b plus the natural log of v to the n. And now I have this guy that looks very similar to the second identity, and I can do that where I pull the n value to become the coefficient in the front. Now, how does that really help us though? It helps us if you look at that equation, doesn't it look very similar to a y equals mx plus b equation? So if we graph this on a graph, we could graph on the y-axis the natural log of the weight, mass times gravity. On the x-axis, we can graph the natural log of the velocity, and then the slope of our line is going to be that n value. So in the lab, you're going to drop varying masses of the coffee filters and determine their terminal velocities. And on the y-axis, you'll graph the natural log of mass times gravity. On the x-axis, we'll graph the natural log of the velocity. And theoretically, we should end up with a line that the slope of it is equal to the n value, and we can determine what that integer is based off of it. So with the coffee filters, you're going to be given about 10 of them, or you're going to watch the video that has me dropping them. You'll record the number of filters. Then you'll use if you're dropping them in class, you'll drop them from a certain height. Because they hit terminal velocity, you'll just have the position, velocity, and time. So you'll measure how long it takes them to fall, and you can just do distance over time to solve for those velocities. You'll come up with a chart. Use your chart to get the natural log. Use your number of coffee filters and the mass of it to get that graph. And from there, we can determine what that n value is. Happy coffee filter labbering.